Hello everyone, I'm Claire. Today let's talk about addition of the chemical function. So the first addition over here is about the proof of case 1, case 2, and case 3. So someone will ask a question. So it is, why do you say 2 is very different? So you see, so we can break 2 from case 1 to case 2. So we have a different from case 2, but so why our other prime powers don't have this property? So let's see. At the first step here, now case 1, if we have examples, n equals 70r, and case 2, of course, it's 2dr, and if it's 70r, then the first time we need to use Euler's torsion theorem. Now here it's 86 equals 1 plus 7h2. Okay, then here, it is a equals actually it's 81, and then it's equal to 1 plus 2h2. Then this one is both sides to the 7, and here both sides squared. Now both sides 7. Here's 86 times 7. Now this is 5 of 72, and okay, the step right here we can have 1 plus h3 72. So this is still also theorem. Then because here it is 5 of 72 and here just 72. But here is very different because in this step we can have this guy, and if we times out we have this, and then because we have h2 times h2 plus 1, and this is a trick. And if we let this part over divide 2, and that's a binomial coefficient. And because if we divide 2, so we need to change 48. Now that's 1 plus 8 times binomial coefficient h2 plus 1, 2. Then we can equal by definition, and that's equal by definition to 1 plus 8h3. Now it's 8, so it's 2d3. Now here it is 2. Then 2 is 1 over 2, 5 of 2d3. Because 5 of 2d3 is 4. Now here's 1 over 2. Then if you try to the next step, you can't create another trick like this, or change to 1 over 4 or something else, you don't know. Well, you don't have this, you can't create this trick anymore, and you only can create the trick over here, then the next step, and the next step, and so on, every step. Now it's this relationship. And now a to this power, now the exponent of a over here, it is 1 over 2, 5 of the modular number. Okay, now here, this step we can't even create a trick, so the next step, then the next step, so on, you can't create any tricks out. Then it is always Euler's 0. Then that's why we can say lambda. So it's case 1 and case 2. What's the difference? Now case 1 is lambda of n equals 5n, and case 2 is lambda of n equals 1 over 2 5n. So what about case 3? Now something we're going to add is when n equals 15. Now this example, the one we're going to add is equal to 3 times 5. Then here it is, I'm going to write out 2 modular arithmetic. Now the first modular arithmetic is a to the lambda of 3 congruent 1 mod 3. Now, and another one is a to the lambda of 5 congruent 1 mod 5. Now, because case 1 and case 2, we can try, so lambda of 3 and lambda of 5 is equal to it is equal to 5 of 3 and 5 of 5. So here now, if we can change we can change them to Euler's theorem. Then the domain of A is what? Is we only let A is common with 3, and A is common with 5. And these two domains, and their same part is when A is co-prime to 3 times 5. That is A co-prime to 15. And we pick from these numbers from the domain 1 to 15, and that's the numbers that we want. And this is the numbers that when you think about A, then the power we need to change is the same. Then it will be least power, then that's least common multiple of lambda of 3 and lambda of 5. Then it's congruent 1 mod 3 and also congruent 1 mod 5. Then we can change it to 8 is the least common multiple of lambda of 3 and lambda of 5, congruent 1 mod 15. So from this step to this step, why is this in the first video I've already talked about it. Okay, so this is the first part I'm going to add. Now, the second part is actually in the chemical function, we have another theorem. We the theorem that we were talking about over here is always theorem 1. And the theorem 2 of a chemical function is one thing. If G is a primitive lambda root. You know what's primitive lambda root? I've explained in the first video. Now, if G is a primitive lambda root, then there are 5 of lambda of n primitive lambda root that are congruent to a power of G. So this thing we can't actually prove it, but let's think about what it is actually talking about. Then let's see about it. So first we can have an example about n equals 15. Now n equals 15, then lambda of 15 is equal to what? Is equal to 4, right? So 5 of 4 it is 2. Now let's see. Now what's the next step? Now let's figure out those number or coprime of 15. Good. Now first is 1, then it's 2, 3 is not, and 4, 5 is not, and 6 if it goes not, and that's 7, then it's 8. Come on, 9, no. Nope, and 10, nope. Now it's 11, then 12, nope, and that's 13. Now 14, of course, because 14 is 2 times 7. Good. It's just these 8 numbers. Now, let's figure out. So 1, any power that satisfies. So we need to think about these guys themselves. What are their least exponent when they're congruent 1 mod 15? Now 2 it is 4. Now 4 it's 2, and 7 it's 2, and if it's 8 then 4 and 11, 2. Sorry, here's 4. Now 13 is 4. Now this is 2. Now primitive lambda roots, it is 2, 7, 8, 13. You find it, right? Okay, so what's the relationship? What's the rule over here? It says when the power over here, it is what? It is the power that our true answer is. Now this is a ruler. But, so you say, hey, so what about, so we can explain what does this actually means. Now, what does 5 lambda of n actually means over here? Now let's see, it's equal to 2 now. Then let's find it. First, we can find a relationship for 2 and 8 and 7 and 13. You'll know why, okay? These two guys and these two guys. Okay, now first 2 and 8. So now 8 is actually equal to, it's equal to 2 to the 3. So first let's write 2 to the 4 congruent to 1 mod 15. Now, and that another one is 8 to the 4 congruent to 1 mod 15. And this is a cycle. And these two numbers are in a cycle. So these two numbers are 2 elements from a cycle, one cycle. Well, every cycle over here only have 2 elements So the amount of the elements of one cycle means the value over here. So why we say these two guys are in a cycle, in one cycle, because if we have 2 to the 4 congruent 1 mod 15, that means a to the 4 congruent 1 mod 15. So let's prove it. Okay, so first 2 to the 4 congruent 1 mod 15. Then we have what we have. Now we have what? We both side to the 3. Then we have 2 to the 3. Sorry, 2 to the 4 to the 3. Now this is actually equal to 2 to the 3 to the 4. And just opposite where they're staying. Now, then this is congruent 1 mod 15. Now we can change this back to here. Why is this? Because we know the condition over here is 2 to the 3 congruent 8 mod 15. Okay. Now we have this over here. 2 to the 3 can change to 8. So now it's 8 to the 4 congruent 1 mod 15. Now what about another one? So 7 and 13. 7 and 13 is 7 to the 3. Now 7 to the 4 congruent 1 mod 15. It's not like these two guys are equal to, okay? Equal to each other. Is they are power each other. That means one of this value to a power is congruent to another power mod n. Good. Now here is 7 to the 4 congruent 1 mod 15, and another one is 13 to the 4 congruent 1 mod 15. Now what's the next step? The next step over here is, of course, we can change this to both sides to the 3. Now it's 7 to the 4 to the 3, and then that's equal to 7 to the 3 and to the whole thing to the 4, and that's congruent 1 mod 15. Then we can change it back to this. What's the reason? Oh, let's tell us. Now let me tell me. Okay, what's the reason? Of course, that's because 7 to the 3 congruent 13 mod 15. Good. That's the reason. Right? Okay. This is the reason. We can change this to this because we can change this 7 to the 3 to 13. Now it's like this. Okay. Now, if we're going to try this, now we know 2 and 8 are one cycle, and 7 and 13 are another cycle. Then in one cycle, we have how many elements, the amount of this element is. What does it mean? So you see, you can see now the amount right here. Now maybe you'll ask, okay, you see in this example, how many cycles are also 2? So does that mean this is the amount of the cycle? So the question is, it is the amount of the elements in one cycle or the amount of the cycles? So the answer is the amount of the elements in one cycle. Because if we can try another example, then another example is when n equal to 9. And lambda of 9 is equal to 6. Okay. Now let's see. All right. So these values are 1, 2, 4, 5, 7, 8. So 2 it is to the 6, and 4 is to the 3, and here's to the 6, and here's to the 3. Here's to the 3. Now tell me which guys are. Now 5 of limit of 9 is equal to 2. Now tell me which two guys are. Of course, you know, right? It's these guys. Okay. Now I don't write those guys. I just write down a relationship, okay? Because the proving is actually really similar. I don't write it because actually you know how to prove. It's very easy. Now the relationship is 2 to the 5, then that's congruent to 1 mod. Sorry, not congruent. 5 mod 9. Good. Now this is their relationship, so we can't prove it now, but actually if you want to prove this, we need to use the group theory. Now we know what this actually means. It means if we have, see what it actually means. If we have a primitive lambda root called G, and we have phi of lambda of n elements, including G, is in one cycle, right? Then we have some cycles, and then all of the elements in all of these cycles, all of them are all of the primitive lambda roots. So we're gonna add these two things. So we know this actually is called Theorem 2. Now here is we're gonna prove it's Theorem 1.